We'll do it. I just thought I'd show this while we were waiting. This is a very generalised outline what sort of thing we'd be expecting for the final report. So the document's up on edX, and I've also put in discussions a link to my Google Drive where you can copy. This doesn't mean you have to stick to this format. It's just what we would normally do for our master's students here. They generally write a full thesis, but it's along these sort of lines. So it's got an introduction, general things, what is the problem you're trying to solve, why is this problem important, what's your approach to it. Then we have our background or literature review, market research. Now this can come directly from your market research and costing report, but it does include the costing bit. Next section is on how you designed it, the project plan and how well you stuck to that project plan, whether things did or didn't work. Evaluation testing and an evaluation of the progress you've made. So the limit we've set is less than 20 pages if you possibly can, not counting table of contents here and the, if we go to the end, references, like so in the end. All right, so 20 pages of actual content. I won't go through it all, but I'll just point out a couple of things. This is just one top way of formatting. You can number the chapters, you can just have them as titles. It's not really critical at this point. Writing, it should be written in the third person tense, which means you don't use the words I, me, you, etc. and things you've already done, so you should be writing as if it's done. Okay, so in the reason we're doing this is if anyone is going to carry on and do the master's program here, you will need to write a full thesis, and this is a way of getting into the right format of writing. So there's things I'm referencing. I've just used IEEE, but if you're familiar with another one, you can use that. And there's some links to how to do the formatting. IEEE is very, very simple and straightforward. Each have a little summary in it, which is just that particular section. Review market research, you can take pretty much from your previous one. The design methodologies, there's just a few things in here. How to label some graphs, they're just random graphs. And how to draw things out. Okay. And as an example, conclusion of a past report in there. All right, so that's all of that's available to you. Like I said, link is on the discussion boards. I've asked for it to be posted. We're a little short-staffed in our edX support team at the moment, so but the link is there, and if you can't find it, just email me and I'll send it directly to you. How's that looking?
Yep, I think we've got it.
Okay, here we are. We're at our 5th of our seminars. A reminder again that these recordings, these meetings will be recorded with the link put on edX. We'll go through the requirements for the next 2 weeks, which is actually very, very little. You should be working on a prototype and thinking about getting your reports started. Now is a great time to raise any unanswered email. I hope we've got to everyone. If not, no. You should also have received feedback on your market research and costing plan. If you haven't or you have queries on it, please let us know. They are generally very good. Savash was the gentleman who ran through those. Thank you, Savash. So please let us know if you've got any queries on the results from. Okay, as I said, the fundamentals of everything that we needed to cover have been covered, so now we're on to individual project time. It's time to contact us if you've got questions, if you want to move forward on any sort of development. Feel free to send an email through to that IoT Capstone email address. Okay. Right. Also, all of the videos have been marked. If you click on that, get back to us. You should have received feedback as well. One of the things I've done just to possibly keep in touch and maybe we can offer a little bit of assistance is I've created a Facebook page. I'll bring that across here if you can see it. There we go. And this is a group for all of our past students who have completed the capstone project. If you want to keep in touch with people, like the page, and as we move along, we'll start posting some things up there. But it would be nice to keep in touch with you. We've been very impressed by the quality of the project so far. So would like to know how you get on. Okay. There's a link to that Facebook page. Go to. Right. So what are we going to look at? We're going to have a look at moving past the, what I like to term, Savash's sticky tape prototype. You'll see why I meant shortly. So once we've done our proof of concept and we've got an idea that the concept that we have has a reasonably good chance of working. We know the algorithms are okay. We know that we can actually sense the data we want. We know we can transfer it to the cloud for our later data analytics. So in principle, we're ready to go with the product. But there's a mid-range step before we actually go to a full production run, which we'll talk about as well. But to get to the point where something is a saleable, marketable, reliable, and it's a big underline on that one, reliable product, we need to have some other tools. To get to this point, or the point of production, we need to have good development tools for the software. And when I say good development tools that are designed for production software, and I'll talk a little bit about why things like the Arduino IDE aren't really that suitable for it. If we're producing some hardware, quite often, if it's a larger run, we'll want to design our own printed circuit boards, and I'll have a look at some of the tools involved. There's different levels we have for the kind of you're doing and the level of complexity, etc. you need to go to produce something that's suitable for your project. And the last thing we'll look at is producing the case, something to hold it, and hopefully that's showing up. There's a wonderful little 3D printed case we did for an ultrasonic guide for blind people. But there's a wide variety of ways you can produce the housing, and they have different reasons for using different types of methods. Okay, so we'll start with the software, and we've probably all used the Arduino IDE, or I hope we've all used the Arduino IDE or something similar to it. And it's nice. It's great for just getting to see if something will work, using a fairly standard or very standard board to try out the software you're developing. It's very easy to debug. So when there is a problem, you just stop, change it, recompile, send it back down to the Arduino, and off we go. Huge number of built-in libraries, so you write all of the code yourself. Very quick to change things. If you want to change platform from a Nano to an Uno, you just change the box you've selected and off it goes, recompile. It works on that board. However, the problem is it is extremely inefficient. Because it's written to be able to handle a wide variety of processes, a wide variety of different types of boards with different output on them, different I/O, different connectors, uses different protocols. It has to be very general. It means that everything is written in a rather inefficient way. So if you're looking at creating software that is either very small, as in the amount of memory it will take up, or very efficient, so that it's not unnecessarily using processing power, which number one means you need a more powerful processor, but number two, and probably more critically in the IoT, the harder the processor works, the more power it draws, therefore the shorter the life of your battery if it's a battery-powered device. So again, efficiency in the processing is critically important to be able to the efficiency of the code that you're running. You raised a really good point about turning devices into sleep mode and saving power that way. Would you like to just talk about that again?
Sure. So one of the things we usually do, specifically with embedded systems, is you're constantly will end up having a loop that you're waiting for an event to happen. And when that event happens, you do something else. Say you're waiting for a very, very simple thing, waiting for a change in temperature, change in pressure, and then when that happens, you want to turn on a danger light, you want to do another action. So the problem with this sort of programming is you're constantly consuming power to wait for something. So one of the best ways to overcome that is you put your system in a sleep mode. So you turn off some of the peripherals of your microcontroller that you don't need off. So that's going to be sleep mode. And then when an event comes in, so that change in temperature, that change in pressure, that can be an interrupt. And so with something like that, what you need to do, you have to stop the current flow of your program, go handle that interrupt, and can come back. Now, this sort of implementation is requires such a low level access to your memory and low level access to the way the instructions in your program are being executed, which is just not possible with Arduino's programmer because everything is kind of abstracted out. But with something like IAR or Code Composer that Ian currently has showing, you can mix assembly language and C-level language. You can look inside your registers. You can have a look at your memory block. So you have such a finer tuned control over that low level of access to your memory. So those sort of programs can be implemented much more optimized.
Thank you. That's one of the main reasons I want to use something a little bit more professional. I've just brought up a screen capture of Code Composer Studio, which is a package designed to instruments CPUs, MSP 430 mixed signal processor showing up there. And as you can see, it is not a simple interface anymore. Using a large variety of directories we have set up, debug information, your source code, are, and it will produce very, very efficient code. We can, as Savash mentioned, include assembly language in here, and in case you haven't used assembly language or you're not familiar with it, a compromise between the binary that a computer uses and language that people use. So each one of these instructions is actually a series of, or translates into a series of ones and zeros directly. So this is, if you read the binary code program, this DC octal would be a particular bit pattern. The equal isn't, but the decimal here would also be a bit pattern. So it's as close as humans can get to working in machine code now, which means it's extremely difficult. Not only do you have to know the language, which is always processor specific, so ones on ARM are completely different to the machine language, assembly language on Intel processors. You have to be also familiar with the hardware architecture of the CPU itself. And that's why we have here a block diagram of the hardware architecture of the MSP 430F2013. So this is a very difficult language to work in, but it is extremely efficient because you're talking at the same level as the computer works at. So you can load registers, change registers, adjust memory, work with real pointers. If you're familiar with C pointers, this is actual direct memory allocation that you can work with. So fortunately, very complex, these packages, no matter what language you're using, and this is using C with some embedded assembly. But it is a very complex application to learn how to use. It's really only for very expert embedded systems engineers, but it's very, very efficient. The other issue with this is it's also very, very expensive. You can get student versions which allow you to have a small amount of code. What is it for the MSP 430s? Savash, you know?
The name of the program?
No. How big can the program be?
I think it's about
4K?
it's still in order of kilobytes. Yeah, 4K, 5K.
So a 4K compiled program is usable, but it's not something you'd use in a complex system. If you have to buy it, it costs thousands and thousands of dollars. So not cheap. All right, so if you're going to go to a full production, large run environment for your IoT device, moving to something which is very efficient is something you would have to do, but bear in mind you would probably have to, unless you're very good at it yourself, hire a embedded systems engineer or get a to develop it for you. So in the software, we've got these sort of ranges. There's lots of things in between. There's GCC, which is the Linux compiler, does lots and lots of different languages. It's a purely command line, so it's difficult to use, but it's free platform. And IAR is one that Savash mentioned. That's another very good one for embedded systems. But there is a lot around, some cheap, some very expensive, some free. All right, so pick the right development environment for what you're doing. So once we've got our code written on for our particular process, we might want to go away from what we have here. This is the one I like, even though Savash is not responsible for this particular design. I like to refer to it as Savash's sticky tape prototyping. And we can see that this is actually made up of off-the-shelf boards. This is what we expect you guys to be doing at the moment. So we've got I think this is an NFR 2402. We've got an inertial unit sitting underneath that. We have an Arduino board and a battery, a little bit of Vero board with a connector and a couple of switches on it, and then these boards together. This is great for proof of concept. The architecture is very similar to what we would end up using. But it's, number one, very difficult to assemble. It's not reliable because these sort of wires break off all of the time. It's messy, so if you had paid good money for a device and you opened it up and you found this sort of mess inside, you wouldn't be terribly happy, because you can see that it's not properly produced. It's not going to be reliable because it's got all the tacked on and sticky taped together. So what you want to do is, once you've proved that this system will perform the function you expect it to, you want to turn it into something a little bit more professional. So I've got two examples over here. This one is a board that takes ASCII output, the serial port or the USB port, and speaks it. So it's a speech engine. Spanish, German, English, Farsi, and a few other languages that we developed here. And as you can see, loose wires hanging off it everywhere. It's all laid out in a nice, clear form, shaped to the shape we needed to put into the box that we were using. It's got no extra connectors, so we can actually reduce the board space, the real estate that's being used up, and is meant to be a much more reliable device. This one here is the first prototype of actually this ultrasonic thing that we built. We just changed. But again, it's the same sort of thing, except with sticky. We're just doing things quickly. But this reduces the, and it does require the tools to take from this over to these. So how do we do this? Well, there's lots of different packages we can use. And the first one we look at is one that I particularly like, actually. It's called Fritzing, and it's similar sort of environment to Ting, except it doesn't do simulation. All right, so we'll get out and show you some examples of that fairly shortly. But we've got the ability to wire up a breadboard, like so. From that, we can get the schematics. Critically important for engineers. When people are designing real circuits, we don't design them like this. Makes it easy for us to follow. We work on this diagram, or this style of diagram here. It gives us the actual resistor values. We can see what the components are. We can see logically where the pins are connected, etc. And from this, we can into a printed circuit board. And Fritzing will automatically create this printed circuit board. You can adjust it if you like, and we'll have a look at that very shortly. And you can write your code within Fritzing as well. As I said, it's not a simulator, but you can send that code down to a connected, real physical Arduino board or other board that you have, and actually test out to make sure that your design is, in theory, working. You can then just here and send it off to their sponsor to fabricate the board. So we'll get out and have a look at, very briefly, at fritzing. I'm sorry about this. I had it all open. Here it is. Okay, so here's Fritz. That's the web page, and I'll just close on me. There we go. It does say it's a beta, but it's the latest version. And we'll that one I was using before. Okay, so we'll go back to the breadboard. We can have our breadboard here. We can alter things if we like, move them. I'll go resistor. There we go. If we can move things around and move it between the connections that we want. And you, as I said, you lay it out very much like the things it does that Tinkercad doesn't do is if we go to the schematic, we can actually see how all the pins are in on that. Make it a bit bigger. So we actually get the pin names rather than trying to work on what we don't know is happening here, just on the I/O that's there. From the schematic, we can then produce a PCB, and it calculates this for you. If you hit the auto route, it'll recalculate the path. So if I move the temperature sensor over to here, and we hope that auto route will fix it. Fortunately, it doesn't. So this is why we have to do things manually at times. Back down. Okay. We can see both sides of the board. In this case, it's only a single layer board. But one of the time-saving advantages of this is we can just click on Fabricate. And we upload the project that we had. And there it is. It's our boards will look like. And we get 3 of these beautiful boards, as they call them. We haven't put any parts on it, but we could. There we go. And it would cost us €26 to have these 3 boards. Now, that is actually quite expensive. We had a whole bunch of boards made for Savash's favourite project, the solar car. They're about 3 inches long, 75mm by 12.5mm, thereabouts. And we got, I think 9 of them would fit on the piece of printed circuit board material, so 9 made. And they cost us 99 cents. Not 99 cents, 99 cents 9. So that was really, really cheap. It was $25 delivery. That didn't matter, they were still cheap. So by going to other manufacturers, you can get them much cheaper. Usually they're fairly good as well. But fritzing, and we're showing it here, great for hobbyists or early to trying out PCBs, but a little bit expensive. So we'll go back to here. Fritzing is definitely worth the shot, particularly as it's free. Okay, so when we move to a more serious production level, there's lots of things that fritzing won't do. For example, it's only a layer board. So you can have a layer on the top of the board and a layer on the bottom of the board. That's it. Quite often what you want to do is have more layers on the board for things like ground planes to reduce noise. Maybe it's a complex or very dense pitch on the circuits themselves, so lots of pins in a given area. So you'll need to have multiple layers, and you need to move to something a little bit better. So the next step up is the Eagle, and that's from the same people like Tinkercad. There is a limited version available for hobbyists that allows you to have 2 signal layers and a 80 square centimetre board size. But the nice thing about this is scalable. You can buy it in different versions that suit the level of complexity of your job. So you can start with a free, get a slightly more complex design that you want to do, then move to a limited license, then professional license, then all the bells and whistles. It's also a platform, which is great, so you can run on Linux and Windows. Not sure if there's a Mac version, I don't think so. But, you can run it on both Linux and Windows. And it's a little bit more complex to use, but it does give you a much control. One of the things these will also do is that auto route I pointed out that we still had tracks crossing each other. That normally means the auto route is not particularly so you've got to do a lot of manual adjustment. When you get to these more professional type packages, the auto route function works much better and makes it better decisions. So Eagle's another good one to look at. Copy, have a play with it, and it's actually quite good for laying out. Then we move to what are really the top of the line. Now, these packages are extremely complicated to use. We used to run courses here for a particular one called Altium Designer. And they were for experienced PCB designers, and the course itself just to use software, not about PCB design, just to use the software was 7 days long, 7 full days of training. So they are very complex, but they do lots of really, really... we can have our bill of materials, which some of the others do as well. Hotspot mapping, so we can look where the power consumption on a board is, see whether heat is being generated and build heat sinks into those particular areas. It does some things on signal timing as well, so it does quite a lot, and can even produce a 3D image of what our finished printed circuit board would look like to make sure that it's going to fit the housing properly. The physical layout is rather important. Drawback here, as I said, extremely and cost. Last time I checked, and this might have changed, there's a bit of competition coming into the market. Altium Design full version costs $25,000 per seat. So every person who's using it, $25,000 for the software. So not something we'd look at lightly. But as I said, extremely powerful, interesting software that can do basically end-to-end production of the electronics. Has no code attributes in it. It doesn't do any simulation of the code or the running of the device. It does allow you to look at the hardware in amount of detail. Okay, so that's for the so for the PCBs, the last little bit is some of the packages will link to manufacturers, such as I showed you with Fritzing. Most of them won't, because they allow you to do that yourself, and they require what's termed a Gerber format file. Gerber is an old, very early, it was a vinyl cutting machine actually, but a manufacturing device. It would cut the tracks, pattern for the tracks for you. Yeah, they're from the 90s. I used to actually fix those machines many years ago. So this particular type of file is used for the layout of the PCB, so you've got to make sure that you can export in the correct file format. There's lots of online stores for produced PCBs. You've got to be very careful about who you're choosing. Who did we use last time? We used PCB and one other. Can you remember who it was?
I think all PCB.
All PCB. Yeah, it could have
one.
been. Anyway, they can be good, but yeah, tends not to be have quality control. Again, you're getting what you pay for. So our 10-cent PCBs, they were good. They actually worked. When you get the PCBs manufactured and you find out you made a mistake once you've assembled them, things can be rather expensive to fix because you've got to go through the whole process again to fix it. So you've got to be very careful when you get the boards produced that you're got them as right as you possibly can. One of the things you can do, and I'll go back to that particular slide, this one here. This text-to-speech engine, we got manufactured, the board made in China. They put all the parts on for us. They ordered the parts, got them in. assembled it, sent them back to us, and it was really, really cheap. I can't remember the exact price a while back, but it turned out they were about $25 each when we bought 100, 200 of them. So that made them really, really cheap. The problem was when they arrived, used the wrong crystal here, which was too tall. In fact, I've got one. I'll just grab it. I'll show you. So when they delivered it to us, if we look here, it was meant to have a half-height crystal, which would have much lower, about the thickness of my finger there. But they didn't. They used the wrong one, and that meant these wouldn't fit in the box that we'd made for it. So we had to go along and pull all the crystals off and put different ones on. The real problem with them, though, was 20% of them didn't work. All right. So again, it's a quality control issue. It was extremely cheap to have them produced, $25 with all of the components on there. However, we had to either try and repair or throw in the bin 25% of the product. So keep that in mind if you're ordering in some of the cheaper production areas. The quality control may not be good, and you're taking a bit of a gamble, but it can save a huge amount of money. Those other ones we had quoted, again for the solar car, Savash, was $4,000 for how many boards?
For, I think it was just 10 boards.
And that was a local manufacturer, which would have been very reliable. We could have had it done very quickly, even though the Chinese manufacturers tend to be very quick as well. But they're pricing themselves out of the market. We know we wouldn't have had any problems. It would have been easy to fix up if something had gone wrong, which was very unlikely. But boy, are you paying for it. The delivery from China was really, really quick. It was within the week. Delivery times aren't really an issue with the cheaper manufacturer. Okay, but just bear in mind the UA. Oh, there we go. I did have it there. So that's just the kind of information you put on for particular boards. This is PCB GoGo, one that we've used several times and haven't really had an issue with them, but very, very cheap and quick. Okay, so the last bit I wanted to touch on getting ready for true manufacture is important. It's what the customer will see of your design. Right? They're not going to open it up generally. They're not going to look at how nicely you've laid out the PCB. They won't see if you've written your software correctly and in a well-structured, efficient manner. What they will see is the box it comes in. And there's lots of different ways of manufacturing depending on the market you're going for. What we've got here is some examples, and I'll go from the cheapest, easiest first. Jiffy boxes, which are these little devices. These are off the shelf, ready-made. You put your board inside, perhaps cut some holes in the side to fit the ports, screw it down, and there's your device. These are great for very small runs because these boxes are actually very cheap as well. And the customer isn't really going to be looking at it all day. So if you're doing a automated watering system for home gardens or farmers, you could pop it in one of these weatherproof boxes and put it out in the field. Nobody would care because it doesn't have to be that pretty. So this is a good, cheap solution. You can get them, as I said, weatherproof. You can get them for electrical outdoor standards. And they're off the shelf, always available, dozens of different manufacturers. So they have a place in the manufacture process. But you wouldn't use them if you're going, because there's much better ways of doing it. The next way of doing it is 3D printing. Now, I've picked a particularly bad 3D print here for a reason, to show that the quality is not always great. Here we can see that you can individual layer of the print, so it's a rough sort of finish. That textured top is not done as a design improvement. It's actually the pattern you get from where the device or the case was sitting on the 3D printing table. We've got some warping. So if we look here, the gap here is slightly different and increases in size here, which is very common in 3D printing. And generally, it's a nice shape. It's the shape we want, but the quality of the case isn't great. So we can get better 3D printers, but usually that means printing, and that's the disadvantage of 3D printing. You can try a case out, you can see if it works, modify it easily. It's very, very cheap to produce. A kilo of plastic is between $20 and $40, which makes an awful lot of cases. But the quality is very variable. The time involved in printing each case is extremely long. You'd look somewhere between 2 and 4 hours to print that little, looks like a Raspberry Pi case. So you can't produce large numbers. However, you can produce the exact copy of what you want to manufacture, use it as a manufacturing or design prototype, and I'll speak very briefly on those shortly. Get the concept, make sure everything fits before you actually go to a different form of production. Next way is vacuuming, and here you can get very high quality products out of it. It's relatively cheap to produce. It has to have a mold made for it so that when you heat the plastic, you pull it down over the mold and you force it to fit by vacuuming the soft plastic over the mold. So these are quite cheap, can be quite robust, but they're not generally used for large production runs. Top way, if you've got very large quantities of making things, is injection molding. And we've got an example of a chess piece here that's injection molded. It's basically a mold works liquid plastic into, or liquid material into the mold, and it forms the that you want to produce, and that can be done for boxes and things as well. The problem here is that the component that you're producing is extremely cheap. The to run it isn't. When you want to do a run of injection molding, you're looking at tens of thousands of devices that you would need to produce before the manufacturer would even turn the machine on for you. So it needs to be very, very, very high. The other problem with it is that causes it to be high volume is to make this mold, and I used to have a company that made these things, you have to produce something like this, and it's a two-piece steel structure that is in two pieces so that it can come apart. You can push your finished product out of the mold itself. Something like this, would be in the vicinity of $10,000 to $40,000. We're talking Australian dollars, of course. So that cost has to be amortized over the entire production. You need very, very high production runs to warrant using injection molding. However, the quality is extremely high, or can be extremely high. The cost is extremely low, but you just need those quantities to make it worthwhile. And which one of these you use is entirely dependent on the desired quality, where it's going to sit, and the production run. So you've got to look very carefully at that. Okay, so that's the getting to manufacture part that I'll talk about, and we're going to go a little over time, but we started late, so that's not a problem. Over the next week, we will be talking about GP application-based services. Dr. McKeegan will be doing that for us, except for the talks where he's teaching, so I'll have to do that talk. And he'll cover how to use GPS, how to include it in your IoT device if it's suitable, how to do mapping and other things. From that, it's actually the end of the course. So you should have submitted your final report. Everything should be done, but we've got to keep the course open for another couple of weeks so that we can mark it and get the results back to you, make sure everything's cleared up. So during 2 weeks, we will continue to have these discussions, and during that time, Dr. Valerie Maxwell will be talking about big data, how to use cloud computing and other issues along those lines. So we'll be meeting with you right up to the close of the course in week 14. I think from memory is September 29th. Sorry, I can't remember exactly, but it's about 4 weeks away. Okay, so that's me. Stop talking, luckily for you. How are we going? Has anyone got any questions? Oh, I was going to show you. Waiting for questions.
I haven't seen any questions coming through, but while you're looking for that, I just posted a couple of links while Ian was talking to IAR, to Code Composer, Fritzing and Eagle, if anyone wanted to kind of take a look at those programs.
Manufacturing prototypes. These are used often to develop a mock-up, if you like, of the finished device. It may or may not actually function. It allows you to work out how you're going to assemble the device, does everything fit together physically, etc. And here's a great example of it. Nothing to do with IoT, but something I do like. This motorbike is largely 3D printed. That doesn't mean it works. But what it does is it allows them then to look at how will they assemble the end bike. Does everything fit together? It's used as an example. They can produce their brochures and other things in the tooling and the assembly requirements. So they produce what looks like a real bike, but it is a full-size replica. And down here, we can see here is parts of the motor being assembly. They check out the wheels and the engine casing and the crank. Looks like they fitted it in, and then mock it up so it looks real. But they can make sure all the parts actually fit together properly, and it does fit in the mountings for the bike. So again, it's the same sort of, at the point where you're going to go into large-scale production, you try and produce something like this for the people that will actually be doing the manufacturing. They can see what the end product is meant to be like. It may not be a functional model, but it does have the physical dimensions and the end quality that you're expecting. And I hate to think how long that would have taken to 3D print.
I just a quick question. Do we need to build everything from scratch when prototyping?
No. It's
I see.
like all real engineering. If you can use someone else's device with permission, and I do actually mention that in the document. Just share my screen again. My mouse battery went flat, and I'm using the touchpad. That's really slow to do anything.
These are the development kits, pre-built development kits I'll be using for prototyping.
Yeah, development kits are fine for prototyping. That's good, because something really quick off the shelf, and you can proof of concept in the limited time we had, because it's really only 12 weeks from the very beginning till the very end. We don't expect that you can actually produce the full system, but you should be at a point where you're making significant progress towards producing that full system. Yeah, let me go down here. And it was in here. There we go. There we go. People, companies, developments where it solves the problem will say, as I said, never reinvent the wheel if you have to. But the things to keep an eye on is what sort of licensing is there. If you're grabbing something and they say it's free to use, it's under the GNU General Public License, also remember that license affects your end product. Because in the case of the GPL, they term it copyleft, because it is exactly the opposite of copyright. It will stop you taking ownership of anything derived from something that is under GPL. The changes you make and you make to that software or hardware, because it can cover hardware too, must be released under the same license. Nobody can charge for it. Nobody can take ownership. You can't anyone else from using it, and you must everything that you did. So it means that everything has to be completely open. Doesn't mean you can't make money from it, because you can. It's perfectly legitimate to charge for the hardware itself, or for support of that, or a subscription service for the data you're providing. But it's a completely open system. There's other ones around, such as the Creative. There's Apache license. There's the BSD license. BSD license is an interesting one. Apple chose it for Mac OS because it allows them to keep some bits private and some bits not. All right. So if you're using something, just be aware of the licensing, but please go ahead and use evaluation for getting things going.
Okay. Thank you.
No problem. Okay. Who else was there? Philippe.
That was it.
Mazam's there, I think. Oh, he's gone. Okay,
I think he's gonna come to the afternoon meeting.
Yeah, there's a much bigger meeting in the afternoon. Afternoon for us. Yeah. All right, everyone. If you've got nothing else, we'll close off. But thanks for joining us. We'll see you in a couple of weeks, and we'll mapping GPS and tying in location-based services to IoT devices. I think morning one. I'll be doing that one. I would recommend that if you get the chance, listen to David when he gives his talk on one of the other recordings, because he knows much more about it than I do. But not to the same level he does. His whole job is about geographical information systems. Okay, farewell.